In the last video, we were talking about R combinations, or as I referred to them, R collections, meaning the number of collections without order of R things that can be chosen from a collection of n things. So for example, just to recall, if we took n is equal to 4 and R is equal to 2, for those two, we can imagine a set of 4 things, say A, B, C, D, as we often do, and list the R combinations, the 2 combinations, or collections, 2 collections, would be, well, AB, AC, AD. Those are the ones that all start with, or have an A in them. And then those that don't have an A but have a B would be BC, BD, and then the last one would be one that has neither AB, and that would just be CD. So there are 6 of them, and I have not ordered them because a collection, R combinations or R collections, are only the objects themselves, not with regard to any particular order. So in this case here, using the notation that we've talked about, C and R, this would be C4, 2 is equal to 6 by what we just did above. This last formula we got in the previous video says that C and R times R factorial is the same as P and R. So in this case here, the special example would be C for 2 times R here's 2 factorial is P for 2. Well, we know what P for 2 is. That's 4 times 3, or 12. And sure enough, this is 6 times 2, which is equal to 12 as well, looking at it both ways. So we're going to look at different ways to write this formula first of all, and then after that we're going to do some examples where we examine how we can use the counting formula for 2 combinations for different kinds of applied problems. So let me go ahead and scroll down here. Oh, let me see. So we need to remember how PNR works, and we've got a couple of ways to write PNR. And so that'll come up in trying to write down a formula just for CNR there. So let me go ahead and first of all just note that that says that CNR can be written as PNR divided by R factorial. I'm going to go ahead and write that down below again too, but that's kind of our starting point here. So let's scroll down and do a few of these calculations to get some other formula. So one formula says that CNR is the same as Cn minus R. Now what is at heart here is the fact that if you choose an R combination or a collection of R things from N, you have left behind N minus R. So if we look at say for example collections of size 5 where N is 5 and R is 2, let's consider the case where N is 5 and R is 2 here for this particular computation here, and use our typical A, B, C, D, now E, and write down the 2 combinations. So 2 combinations. I'll abbreviate that here, so because of space. Well, AB, AC, AD, AE, BC, BD, and so on. I'm not going to write them all down. I think we'll get the idea here. And so if I take AB, I've left behind CDE, a 3 combination. If I take A and C, what I have left behind is BDE. If I take A and D, I have left behind BCE. If I take A and E, I've left behind BCD. So these are matched up, each 2 combination with the corresponding 3 combination. BD, take that and you're leaving behind ACE. you see how this works. So what else would there be? BE. If I take BE, I leave behind ACD. If I take CD, I leave behind ABE, etc. So the two combinations match up perfectly with the three combinations. So this, what is left behind are the three combinations. And here R is 2. And here n minus R, 5 minus 2, is 3. And so that works in general. Each R combination corresponds to an n minus R combination. So they number the same. Now you could have done this in an algebraic way, but this is a nice, what we call a combinatorial argument. And so that's a real convenient way to look at it, combinatorial argument. So that's convenient. As we get some nicer formulas for counting these, we'll examine that again later. We'll look at it again. So the next formula I want to talk about is just a pure algebraic formula for CNR in terms of factorials. And this plays off of the fact that we know that the combinations are counted in a way related to the permutation. So we know for the proof here, I'll go ahead and write the word proof here, CNR is equal to PNR divided by R factorial from our previous expression. So that's a letter R right there. Our theorem from the previous video said that CNR times R factorial is PNR. I've divided both sides by that. But we have two formulas for PNR, and one of them is in terms of factorial. So this is 1 over R factorial. And you might have to look back to recall that PNR can be written as n factorial over n minus R factorial. So in fact, that is n factorial over R factorial times n minus R factorial. Now, it's just as easy to get the last one here. So I'm going to go ahead and write that down because we also have the proof that CNR is equal to PNR over R factorial again, but we have a formula for PNR as n times n minus 1 through n minus R plus 1. That was the first formula we developed for PNR, and then R factorial is R times R minus 1 all the way down to 1. By the way, it's interesting to note and helpful to see that there are factors top and bottom here. I want to use these, but I'll cut this clip short right here, and then we'll use these for some examples in the next one.